Bismillahirrahmanirrahim. Assalamu alaikum students. Today's topic is going to be about LRC circuit, where L is representing inductor, which is symbolically represented as a coil. R is representing resistor, which is symbolically represented as like this, and C is representing capacitor, which is symbolically represented as this. And when all of these three components are in a circuit, we call it LRC circuit. So first of all, we have a vector representation of an alternate quantity. Before going on towards that, let's assume that the coil which is producing the alternate current is basically having a whole rotation, and the time taken for that rotation is representing by T, and we represent that T as a circle over here. This is the whole time period for the coil to rotate. We divide it into 4 parts. This is 0 over here. This is T by 4. This is T by 2. This is 3T by 4. That means 3/4 of the time has passed, and the whole time T, which is a time period. Now we have the formula that theta is equal to omega t, where omega is representing the angular frequency. We know the value of omega because it is rotating to a whole cycle, which is 2 pi because of a whole circle, divided by the time period t. So let's put the value of omega in the above equation. What do we get? We get theta is equal to 2 pi over t multiplied by small t, where this t is representing the time period of that coil, and this small t is representing time period at any instant, or we can say instantaneous time period. So if we want to find out the value of radian at this point, this point, this point, this point, and the point again t, we have to put the values turn by turn in this formula, like theta is equal to 2 pi divided by t. So instead of t, I'm going to put in the value of 0. So angle at this point will be equal to 0 radian. Now if we continue, theta is equal to 2 pi divided by t multiplied by t by 4. That is t by 4. T cancel, 2 1s are, 2 2s are. It is pi by 2. So the radian at this point will be pi by 2, which is making angle of 90 degrees. So we can say it is equal to 90 degrees. If we continue, it is 2 pi divided by t multiplied by t by 2. 2 cancel with each other, t and this t cancel. So it is pi or 180 degree. So at this point, it is pi by 2. Sorry, not pi by 2, pi. Or we can say it is equal to 180 degree. If we continue, it is 2 pi divided by t multiplied by 3t by 4. T and t cancel, 2 1s are, 2 2s are. So answer will be 3 pi by 2, or we can say 3t by 4, 3 pi by 2, or 270 degrees. And last but not the least, theta is equal to 2 pi over t multiplied by t, which is the whole time period. So these two cancel out. Answer will be 2 pi or 360 degrees, which is over here, back again. Now, keeping that in mind, the values of time period and the radian corresponding to them. Let's continue. A sinusoidal alternate voltage or current can be graphically represented by counterclockwise. So this has to be remember that every time we have to move counterclockwise, rotating the vector provided it satisfies the following condition. That means it has to be counterclockwise and it has to be moving in the direction of the vectorial representation. Now, its length on a certain scale represents the peak or RMS values of the alternate quantities. We studied that. It is the horizontal position at instant when the alternate quantity is 0 and increasing positively. The angular frequency of the rotating vector is same as the angular frequency omega of the alternate quantity. Now, this can be easily represented in the form of graph. Let's say on the graph, the x-axis is showing the time period, and on the y-axis, we have different quantities. Let's say voltage and current, which are alternating according to these, you can say, conditions. Now, if we divide the whole time period into 4 parts, let's say at this point it was 0, and at this point it was t by 4. At this point the time period was t by 2. At this point it is 3t by 4, and this point it is basically t, or in the form of radian you can say it is 0 at this point, it is pi by 2. At this point it is you can say pi. At this point it is 3 pi by 2 at this point, and last but not least it is 2 pi, just like in the previous slide. Now, keeping that in mind, we have the two vectors. One vector basically which is representing by red color, which is OV. It is basically representing the voltage. And the other vector basically which is represented by blue color, it is OI, which is representing current. And as you can see over here, they both are making an angle of 90 degrees with each other. Now, if they are making the angle of 90 degrees with each other, which is on the same condition as basically shown in the given condition, that these quantities, these vectors are to have a certain scale represent. That means the scale of these vectors are along the graphical representation which we are going to show over here. Now, in the same way, horizontal position of at any instant when the alternate quantity is 0, that means at this point, this is the horizontal position, and we say the current is basically at this point is 0, and graphically it will be also considered as 0. Moving anticlockwise, it will increase as it rotates. So this whole vector, if you can imagine it, this whole vector will start to rotate in the anti-clockwise direction, which was counterclockwise direction, which we represented earlier. So let's apply this concept over here. So as it rotates, as the blue line is representing the current and the red arrow is representing the voltage. So here we go, it rotates. And as we can see over here, the current has increased to maximum value at, let's say, the time was over here 0, and the time over here was t by 4. Again, this is t by 2. This is 3t by 4, and this is t. So as this blue line over here, it basically moved from this position to a new position at t by 4 after some time to maximum value. So it went from here to a maximum value, whereas the voltage, which was red, basically it moved from the maximum position to 0 point at t by 4. Let's continue. So as it rotates again, basically with the angular frequency of omega, this voltage basically goes to the other side, it will be negative, and we can see in the case of current, go back to 0 at the point t by 2 or the time period t by 2. As we continue, it start rotating again in the clockwise direction. The current goes to negative, whereas the voltage over here increase to 0. And last but not the least, we can represent it whole by a graph that I can clear it out so that it is clear to all that this is the graphical representation of voltage and current if the voltage was leading by an angle of 90 degree along all of these time periods, which is 0, t by 4, t by 2, 3t by 4, and t. And so we have represented the condition of all these 3 points. Now, in this case, it says over here, the figure shows the sinusoidal. Figure shows a sinusoidal voltage waveform leading an alternating current by pi by 2 or 90 degrees. The same fact has been shown vectorially in figure. That means at this point, this figure, we can draw it over here, that OV is leading from OI by an angle of 90 degrees. Here, OI represents the peak or RMS value of, or we can say root mean square value of the current, which is taken as a reference quantity. Similarly, OB represents the RMS value of peak value of the alternating voltage, which is leading the current by 90 degrees. Both of vectors are supposed to be rotating in a counterclockwise direction. So we basically showed it to you at the angular frequency omega of the 2 alternate quantities. Figure shows the position of voltage and current vector at t is equal to 0. Now, AC circuits. Now, what is AC actually? AC represents alternating current. Alternating current. Basically, it also follows a sinusoidal pattern like this. Keeping that in mind, the base circuit element in DC circuits basically are those circuits which do not change their polarity. That means the terminals are not changed. They are constant throughout the experiment. And this movement of current is known as DC or direct current. In a resistance which controls the current and voltage and relationship between them by Ohm's law, which is V is equal to IR. That means current is directly proportional to voltage regarding the conditions such as temperature remains constant. But in the case of alternating voltages, now alternating currents, if there is, the terminals basically change after a few time, you can say a few seconds. In AC circuit, the addition to the resistance to new circuit elements, namely inductor, which is represented by L, and capacitor, which is represented by C, becomes relevant. This current and voltages in AC circuit are controlled by 3 elements, which are resistance, inductor, and capacitor. We would study the response of AC circuit when it is excited by an alternating voltage. Now, as it goes along, that as the time passes, the current will flow through this resistor and goes to the negative terminal. And after some time, the terminal basically change their polarity. So this becomes negative and this becomes positive. So the direction of the current also changes as we are following the convention current. AC through a resistor. Now, first of all, figure shows a resistor of R connected with an alternate voltage source at any time, the potential across the terminal of the resistance given by V is equal to V naught sine omega t. So if this is the alternate source and we connect it to a resistor over here, this, and this is R. So for this first time period, the current will flow conventionally like this. But after a few seconds, this polarity will change, and this will be positive, this will be negative, though now in this case, the direction of the current will change. So only the direction of the current is changing, and the polarity is also changing sinusoidally, which we can represent over here. And in the same way, we can say the voltage basically increase and decrease along the time, like a sine function like this. This graphic representation of voltage, where over here it is V naught, there's 0 volts over here, it is negative V naught over here. And the same way, we can say where V naught is the peak value of the alternate voltage and current I, this is I actually, not 1, flowing through the circuit is given by Ohm's law. That means I is equal to V over R of V naught sine omega t, or we can say I is equal to I naught sine theta you can say, or omega t. So from equation A, we can say V is equal to V naught sine omega t. If we divide it by R on both sides, it will be according to Ohm's law, I is equal to I naught, which is I max sine omega t. So this is the formula which we have gotten over here. Now, keeping that in our minds, let us represent graphically as well. So as we know, we have the whole time period for one coil to rotate, and we divide it into 4 or 5 components. Over here it is 0, you can say it is T by 4, it is T by 2, and it is 3T by 4, and this is T, whole time period. Now in this case, because both of them are following the sine function, both of them are basically represented by a parallel vector like this, and blue line is representing the current, let's say I over here, and the red arrow is basically representing the voltage over here. Again, the same process is there. We have to rotate it anti-clockwise so that we can see at this point the current is 0 because it is at the horizontal position, and the voltage is also 0 because it is also at horizontal position. Now as it moves in the anti-clockwise direction like this, now we can say very simply that the voltage has increased at time T by 4, and the current has also increased by time T by 4. As we continue, we can say the voltage has decreased, but in opposite direction. So the voltage has decreased at T by 2. The current has also decreased by at the point T by 2. So as you can see over here, they both are in phase. The way voltage is behaving, the same way the current is behaving as well. As it rotates again at 3T by 4, let's say the voltage goes to the negative terminal, as it is basically in opposite direction now, and same is the case with current as well. If we continue to the last point, the voltage basically goes back to 0 point again because it is in the horizontal position, and so will the current as well, like this. So this is the representation that is clearly represented like this. Let me clear it out so that it is clear at all points. So this graph is basically showing that the current and voltages are in the same phase, that as the voltage was increasing, the current was also increasing, and as the voltage was decreasing, the current was also decreasing. Keeping that in our mind, we represent it vectorially as they are both parallel to each other like this. V is in red and current is in blue. Where I is the instantaneous current and I is equal to V naught over R is the peak value current. It flows through equation A and B. It follows through equation A and B that the instantaneous voltage of both and voltage and current are sine function. That means they are both following the sine function, which varies with time as shown in figure. This figure shows that when voltage rises, the current also rises. The voltage falls, the current also does so. Both pass their maximum and minimum values. As we can see over here, it is maximum, minimum, and maximum on the other side at the same instant. Thus, in pure resistive AC circuits, the instantaneous value of the voltage and current are in phase. This behavior is shown graphically in figure and vectorially in figure as well. The figure shows V and I vector of a resistance. They are drawn parallel because there is no phase difference between them. The opposition of alternating current which circuit represents is the resistance R is equal to V over I, and the instantaneous power in the resistance is given by P is equal to I square R is equal to VI into V square over R. So we can basically represent the value of power, which is VI. Instead of V, I can put IR according to Ohm's law, which is multiplied by I. So P is equal to I square R. In a similar manner, we can say P is equal to VI, and we can say instead of I, I'm going to put V over R according to Ohm's law. P will be equal to V square over R. So it is the same formula, whereas the value of VRR I is R basically rearranged so that it can be formed like this. P is in watts, and this is the unit of power. V is in volts, which is the unit of volt, and I is in ampere current, and R is ohms basically. It is very important to note the equation holds only when the current and voltage are in phase. That power value only holds, that is maximum, when both of them are in phase. Power loss in resistance. The power curve resistive circuit obtained from the product of the corresponding instantaneous value of the value and current of the, say, voltage and current figure shows the power is also always positive except for point LMN. That means they were at point 0, which drops to 0 for a moment. This means the voltage source is constantly delivering the power to the circuit. The average power dissipation in the resistors R over the one complete cycle of applied is equal to P is equal to average of V and I, as we know that V was equal to maximum V sine omega t and I was equal to maximum I sine omega t. So if we basically multiply these two sine function, we get V maximum into I maximum sine square. So as we have sine square, it will increase the average, because this brackets basically are representing the average value of the sine function. So the average value of the sine function is half, because the maximum value of the sine function is 1. So average value will be 1 divided by 2, the two quantities which we have, which is half. So if we have the half value, we basically divided Vm into Im divided by 2. So we can simply write it down like this. Or we can say that this 2 can also be represented as Vm divided by under root 2 multiplied by Im divided by under root 2. So this thing, this Vm divided by under root 2 is represented by Vrms, and this Im divided by under root 2 is represented by Irms. As we know the formula, voltage root mean square is equal to maximum voltage divided by under root 2, and Irms is equal to maximum current divided by under root 2. And this is what we have done over here. So instead of writing like this, we have written Vm divided by under root 2 multiplied by Im under root 2 is equal to Vrms and Irms, which is the value for the power which we have lost in the case of resistance. Now, alternating current through a capacitor. So if this is our alternating source, and we have connected to a capacitor. Then in this case, when the time is let's say starting at this point, this terminal, let's call it A, is positive and this terminal B is negative. The current will flow in this way and charge the capacitor. So this plate will be positive right over here, whereas this plate will be negative. But as the time passes, this terminal A will become negative and this terminal B will become positive. So this is negative, this is positive. Now the direction of the current will basically change because of the polarity, as you can see over here. Now this will become positive and this will become negative. So it is discharging actually. In this case, it is discharging, while in the first case, it was being charged. And this basically is the whole concept. But this is possible only in the case of AC, in the alternate current. What if it was a direct current? That means now in the case of direct current, we are using the capacitor right over here. We'll see that the current flows through this and the terminal basically become positive. But after that time, no current will pass through because it is already full. So how it will basically go into the conductor which is already full. So no current will pass through after some time in the case of DC current. So no current will pass through. Only current will pass through in the case of AC current. Now keeping that in our minds too, let's basically read more about it. It says over here the alternating current can flow through resistance, but not obvious that how it can flow through the capacitor. It can demonstrate by the current shown in figure A. Low power bulb is connected in series. That means we can connect a bulb over here as well with a 1 microfarad capacitor to supply the main through the switch. When the switch is closed, the bulb lights up. That means if there is a switch over here, we close the switch and the bulb basically lights up because the current is passing through. Showing the current flowing through the capacitor, the direct current cannot flow through the capacitor. As I've told you, that direct current basically cannot basically pass through as the capacitor is full and the current can't change its direction, so it will stop after a while. The direct current can not flow through the capacitor continuously because presence of insulating material between the plates of the capacitor. Now let's see how the AC flows through the capacitor. That means now we are only discussing the process of alternate current. The current flows because the capacitor plates are continuously charged and discharged and charged the other way around by the alternating voltage. That means the terminals basically are changing because of alternating current. The basic relation between the charge Q on the capacitor and the voltage V across the plate, that is Q is equal to CV. We know that as the charge on the plate basically increases, the voltage also increases. So we can say Q is directly proportional to V, or we can say Q is equal to CV, where C is the constant of proportionality, which is known as capacitance, and which is represented right over here as Q is equal to CV, which holds at every instant. V is equal to V naught sine omega t applies the alternating voltage. The charge on the capacitor at any instant will be given by Q is equal to CV, which is equal to CV V naught sine omega. So in this case, we can see very clearly that charge basically is strictly proportional to voltage. So as the charge will increase, the voltage will also increase simultaneously. But what about current? So for this, first of all, since C is basically constant and V is also constant, it is obvious that Q varies with the same way as the voltage. We can say V and Q are in phase. The current in this case now is the rate of change of charge with time. Charge Q with time. So we can represent it mathematically as I is equal to delta Q, the change in charge divided by time. Now, if we want to basically use mathematics in this one. So Q is equal to CV, as we can see over here in this formula, and which is equal to CV maximum sine omega t. Now Q is equal to CV maximum sine omega t, and we know that I is equal to delta Q, delta T is equal to Q. Instead of putting this Q, we put the value of Q in this equation. We get delta CVM max sine omega t divided by delta T. Now, if we look at this one, by using the mathematical formula that delta sine omega t divided by delta T, actually over here, will be equal to omega cos omega t, which is basically the differentiation of this sine value. If we differentiate sine omega t with respect to time, what do we get? The differentiation of sine omega t. So if we apply the formula in this case, so this is the constant value, it will come first, sine will convert into cos omega t, and this is how we got the answer, that omega cos t. So in the same way, let me clear it out so that it is clear for all of you. This is delta T over here. So CVM, instead of writing this whole thing, the sine omega t divided by t, we can say omega cos omega t. And as we know that by the function of sine alpha plus beta, that it will be equal to cos omega t. So instead of writing cos omega t, we can say sine omega t plus half, or we can say half pi or pi by 2. How is this possible? Let's put it and check it out. Is our value correct or not? So let us do it over here. We are using this formula, sine alpha plus beta. Now in this case, I'm going to apply the formula of sine alpha plus beta, which is equal to sine alpha cos beta plus sine beta cos alpha. So over here, we in the case of alpha, we have omega and omega t, and beta, we have pi by 2, which is equal to 90 degrees. But let us put in the values. So it is sine omega plus cos pi by 2 plus sine pi by 2, sorry, or pi by 2 into cos omega t. So as we know, cos 90 is equal to 0. So this whole thing will be equal to 0. Sine 90 is equal to 1. So our answer will be cos omega t. That is why we replace this sine omega t plus half plus pi by 2 from cos omega t. And from this, we can see very clearly that in this case, current basically is leading by an angle of pi by 2, whereas the voltage is basically lagging behind by pi by 2, very simply, because as you can see over here very clearly, that it is sine omega t only. But in the case of current, it is omega t plus pi by 2. That means it has extra value of pi by 2, that means ahead of time. So let us represent it graphically as well, so that it is clear for all of us. And if we represent it, just to make things easier, if we represent the CVM omega with the maximum value of I, which is maximum current. So in this case, we can represent this I, and we can get I is equal to I maximum, instead of writing this whole criteria over here, I maximum omega sine omega t plus pi by 2. So this is our value, and you can see by comparing these two values, Q is basically is also lagging behind by the angle of pi by 2, and voltage is also lagging behind by the angle of pi by 2. Now, how can we represent it? Very simply, graphically, that current basically is leading, sorry, in this case. So blue color is represented by current. So current is leading by pi by 2, whereas the voltage and the charge basically are lagging behind by the angle of 90 degrees, as you can see vectorial diagram of this whole situation. Let's continue and start basically solving these values in the form of graphical representation. So here we go. So here's the graph again. We have divided into 4 components, 4 timelines, which is 0 over here. This is t by 4. This is again t by 2. This is 3 t by 4, and this is t. Now in this case, as I told you, that this blue line was representing the current, which is leading by the angle of 90, and the voltage basically is lagging behind by angle of 90. And the current basically we can say the charge in this case is making a sinusoidal function. So charge, we can draw it by a green color. So here the charge goes like this, the sinusoidally throughout the graph like this. And now we consider the voltage and current. Now in this case, we can represent it very simply by the slope of the graph of current, charge. So as we can see at this point, let's focus on this point. Let's draw a slope over here. So the slope is moving to the maximum upward position. That is why the current is maximum at this point, and the voltage basically is 0. But the charge is maximum. Q is moving towards the maximum. The slope is maximum. That is why we have represented I is equal to delta Q divided by delta T, which is slope of I. It is maximum at this point. If we continue to the point of T by 4, what will happen? Let's see. That means now the voltage has increased to maximum point and current has gone down to 0. We can see over here the slope at this point is 0 and the current has gotten to the point of 0. So let us draw this current now. The current was maximum at point O. It decreased to 0 at T by 4, and the voltage basically increased to maximum value at T by 4. If we continue the same concept, now at this point the current basically has got to the opposite direction, whereas the voltage has gotten to the 0. So at this point, first of all, look at the charge slope. The charge slope is going down. So the current is moving in downward direction. As you can see, the current is in opposite direction now. And the voltage basically in this case has gotten to 0. So here we go, it is 0. And the current is in opposite direction. So let us follow current as well. So it is in opposite direction. Now again, it is basically flowing in the opposite direction. The slope is flowing in the opposite direction of for the charge, as we can see at this point. Now at this point again, the charge basically is showing the slope which is equal to 0. So the current will be equal to 0. If we come over here, that means this line will come over here, and we can predict that the voltage basically will go to the maximum value, but in opposite direction, right over here, just like that. So it has to rotate like this. Yes, it does. And in the similar way, we can say in the next point, the slope is basically now in this direction. That means it is starting to increase. That means it will be at its maximum point. The voltage basically will go on to 0 and the current will be maximum again. So let's see how it goes. Yes, current is maximum now and the voltage is 0. So here we show it that the voltage is 0 and the current basically is in maximum point. So this is the graphical representation, Excel representation with respect to slope. And so the value of I at any instant is corresponding to the slope Q and I curve. That means the slope was representing the value of I. At 0, when delta Q was equal to 0, slope has its maximum. Right over here, slope was maximum, so the current was also maximum. So I was maximum from O to A, and the slope of Q T curve decreased to 0. So I is 0, and from at N from A to B, the slope of QT curve is negative. So the negative of N to R, in this way, the PNRS T gives the variation of the current with respect to time. So in this, we can represent it very clearly like this, that as the basically current basically decreases, the slope was basically decreasing in this the case of charge. So referring to the figure, it can be seen the phase 0 is 0 at the upper limit of pi by 2. So the phase V0 is 0. So the phase over here, the V0 is 0, and the current basically is maximum. But the current at this point is maximum so at its phase is pi by 2. Thus, the current is leading by the applied voltage, which is 90 degree, which is pi by 2. Now, considering the point A and the phase alternating voltage A is pi by 2. That means at point A, the voltage is maximum, reaches to maximum value, whereas the current reaches to the negative. Oh, sorry, the 0 point. But the phase of current N is pi. Again, the current is leading by the voltage by 90 degrees. That means now again the current is leading at all points. We can see similarly by comparing the phase point and BR. That means at this point the current is also leading by the angle of 90 degrees. CS at this point also the current was leading by the angle of 90 degrees. And DT at this point also the current was leading by the angle of 90 degrees. It can be seen that all of these points leads the voltage by 90 degree or pi by 2. This vectorial representation in figure. That means we have represented it graphically as well as vectorially. Now, reactance of a capacitor. Reactance of a capacitor is a measure of opposition offered by a capacitor to the flow of AC. That means current basically passes through the capacitor. So some part of the charge basically is being stopped or being stored by the capacitor. That is why we are saying that it is reactance or the opposition of the capacitor. It is usually represented by XC. Its value is given by XC divided is equal to VRMS divided by IRMS, where VRMS is the root means square value of the alternating voltage across the capacitor, and the term RMS value of the current passing through the capacitor. The unit of reactance is ohm, just like of resistance in the case of capacitor. XC is equal to 2 pi FC is equal to 1 over omega C. That means it was equal to XC is equal to 1 over omega C. So instead of omega, we know that omega is equal to 2 pi over T, because it is angular velocity, angular frequency, sorry. So it is 2 pi F, because we know that time period is inversely proportional to or is reciprocal to the frequency. So instead of writing like this, we can say 1 over 2 pi FC. So this is the formula. According to the equation, a certain capacitor will have large reactance at low frequency. Large reactance at low frequency. We have to keep that in mind. That means if the frequency is low, the reactance will be very, or the opposition, the current value will be very large. So the magnitude of the opposition offered by it will be large, and the current in the circuit will be very small. That means it will take the, if the time period basically is very low or high for charging and discharging, the current will not flow, because the capacitor will be charged fully, and it will not allow the current to basically pass through it. So it will stop the current. So that is why at low frequency, it basically performs as a large reactance. On the other hand, at high frequency, the reactance will be low, and high frequency, the current through the same capacitor will be very large, because it will charge and discharge within a very short period of time. So basically, it will not apply any reactance at all. It will be very small in that case. The power loss in the capacitive circuits. In the pure capacitive circuit, the current leads by voltage by 90 degrees, as we have seen. The phase, therefore, the power curve of the capacitor is the average power loss in the capacitor. That means if we take the averages of these two sign values, or we can say in the case of current, we can say instead of I, it is cos omega t, because it was maximum at 0 point. So it was following the function of cos. So if we take the average of these two, the answer will be equal to 0. So the whole thing will be equal to 0. So the power in this case will be 0 in the case of capacitance. Now in the case of inductor. Now in this case, if we have the alternate source over here, and there's a, you can say, inductor over here, and as the time passes, it will basically go through the inductor, but it's self-inductance. That means when the current passes through it, a magnetic field will be formed, and the same magnetic field will basically, which we know, which is known as induced current, will try to stop this current as a self-inductance. So it is not easy for us to basically use the alternate current in this case, and because after some time we can say that the terminal of this alternate source will change, so the current will also change. So it will not allow certain changes in it, as a magnetic field will not allow to change suddenly. Now in this case we have understood this concept, but in the case of direct current, it is very easier for the inductor to basically, and the current will flow in one direction, so it allows the current basically to pass through. In the case of a DC, the inductor will allow the current to pass through in the case of DC, while in the case of AC it will apply some resistance. Now keeping that in our mind, let's read about it. An inductor is usually in the form of a coil or a solenoid. Basically it is a coil form from a thick wire, so that it has a large value of self-inductance and has a negligible resistance. We have already seen how the self-inductance opposes the change of current. So when an alternating source of voltage is applied across the inductor, it must oppose the flow of alternating current, which is continuously changing. As I told you before, let us assume that the resistance of the coil is negligible. We can simplify the theory by considering the first current and then finding the potential difference across the inductor, which will cause this current. Suppose the current is I is equal to I naught sine omega t, or you can say 2 pi f. If L is the inductance of the coil, and there should be a T over here, inductance of coil, the change in the current setup back EMF of the coil of magnitude EL, which is self-inductance, is equal to L into delta I divided by delta T. That means more basically voltage has to be applied by the voltage source so that it changes its direction as we want it to be. Keeping that in our mind, so what do we do? To maintain the current, the applied voltage must be equal to the back EMF. That means the more voltage should be applied so that it changes the voltage according to our needs. It does not apply any resistance to our given voltage, otherwise it won't work. This applied voltage across coil must be therefore equal to V is equal to L into I delta I divided by T, where L is represented by self-inductance constant, which is L is a constant value and V is proportional to delta I over delta T. So in graphical representation, as the slope of the I will increase, the voltage will be maximum, and the slope of the I will be 0, the voltage will be 0, and the slope of the I will be in decreasing mode, the voltage will be in the negative. So in this case, as we put in the values, V is equal to L into delta I divided by T is equal to, instead of I, we can replace it by I is equal to I maximum sine omega T. And instead of writing like this, we can say L I am maximum delta sine omega T divided by T. This is the same kind of thing which we have done before, which is the differentiation of sine omega T. So if we differentiate it by using the simple calculus, that means delta sine omega T divided by delta T, which with time it is basically we differentiate it as we get omega cos omega T. So representing this omega cos t, instead of writing this whole thing, we get, putting values in the above equation, what do we get? We get V is equal to omega Lim omega t. This whole thing, omega Lim, basically represented by the maximum voltage, which we can get. And if we put the value of Vm in this equation, what do we get? We get V is equal to Vm cos omega t, and as we can use the value of sine alpha plus beta, we can get the V is equal to Vm omega sine omega t plus 1 pi by 2. So in this case, which is quite opposite to that of the capacitor, the voltage is leading over here as compared to, you can see over here, as compared to the current. The voltage is leading by an angle of 90 degrees. So if we have to draw it, the voltage basically is leading and the current basically is lagging behind by an angle of 90 degrees, just by shown over here. You can see very clearly. Now, let's show it by the help of graphical representation again. So at angle of 0, angle of 0, this is pi by t by 4, and say t by 2, 3t by 4, and this is t. So as we can say that voltage is leading from current by an angle of 90 degrees. So at this point, we can say the slope of current basically will show the direction of the voltage as well. So as it rotates anti-clockwise direction, now if we represent it, first of all, we'll just represent the current. It was 0 at point O, at t by 4 it increased. So as we can see that the slope was increasing, the voltage was maximum at this point, maximum. And at this point, at the point of t by 4, the slope was 0. That means at this point the voltage is going to be 0, and vectorially also we can say the voltage is going to 0. And in the same way, we can follow the whole pattern that the voltage basically was leading by the angle of 90 degrees, so it went to negative, whereas the current in this case got to 0. Now let's move this graph ahead. As it basically again rotates in the anti-clockwise direction, the voltage goes back to 0. That means change the color of voltage, so it got back to 0, whereas the current basically got to the negative. And as it moves, as you can see very clearly now, that it is clear from this graph that as the voltage was moving along the timeline, the current was lagging behind by the angle of 90 degrees, or you can say the voltage was leading by an angle of 90 degrees. So figure shows the current varies with time. Now in this case, varies with time. The value of let's say I at t basically is given by the slope it. The curve, the various instances at O, the value of slope is maximum. That means at this point the slope was maximum, so the voltage was maximum. So the value of V was equal to V naught, which is maximum, occurs at O, represented by OP. From O to A, that means from this point to this point, the slope of I decreases to 0. That means the slope at this point basically was decreased to 0. So the V also decreases to 0. So over here we can say the V is also decreasing to 0 at point Q. From A to B, the slope of I graph is negative, so the voltage goes to Q to R. In this way, the voltage represents the P, Q, R as T, corresponding to the current of curve of OA, B, C. By comparing the phase of the pair of points OP, which is over here, OP, AQ, right over here, and BR right over here, and CS we can see, and DT we can see that it can be clearly seen that the phase of the current is always less than the phase of voltage by 90 or pi by 2. The current lags behind the applied voltage by 90 degrees, or the applied voltage leads by the current by 90 degrees or pi by 2. This vectorially shows the inductive reactance of the measured opposition offered by the inductance to the flow of alternating current. It is usually denoted by XL. What is XL? So XL is equal to Vrms divided by Irms, where if Vrms is the root mean square value of the alternating voltage across an inductance, Irms is the root mean square value of the current passing through the XL is given by XL is equal to Vrms divided by Irms, or it is represented by XL is equal to omega L. Instead of omega, we can say 2 pi over TL, and 2 pi instead of T, I'm going to write F. So this is what is being written over here. Now, reactance of the coil. Reactance of the coil, therefore, depends upon the frequency, and the inductance, basically L, is directly proportional to both frequency and inductance, self-inductance. The L is representing Henry, which is F in Hertz, and basically XL is in ohms. Basically, it is noted that the inductance and the capacitor behave oppositely as function of frequency. If F is low, XL is small, but if X is large for high frequency, XL is large, but XC, you can say, is small. The behavior of resistance is independent of frequency. It can increase or decrease regardless. So referring to the figure, it can be seen that no power dissipate in the pure inductor in the first quarter of the cycle. V and I, both are positive power. As you can see over here, they both are in positive quadrant, which means that energy is being supplied to the inductor. The second quadrant, the V is negative. Now over here, the V is negative and the I is positive, as you can see over here. Now the power is in negative. That means we have to apply the power to the system, that energy returned to the inductor. Again, the third quadrant, it received energy, but returns the same amount in the fourth quadrant. That means it is gaining the energy, but in opposite direction, but in this fourth quadrant basically gives back the energy again. Thus, there is no net change of energy in a complete cycle. Since an inductor coil does not consume energy, the coil often employs for controlling AC without consumption of energy. Such inductance is known as choke. Impedance. Now, what is impedance? We already know the resistance R opposition to the flow of current. In the case of alternating and induced inductance L or a capacitance C also offer opposition to the flow of AC circuits, may consist of resistance and inductance, capacitance, or combination of these elements. That means this is the combination of these elements. When they combinedly form a resistance, this is known as impedance. The combined effect of resistance and reactance, that means resistance plus reactance, which is the resistance offered by capacitance and inductance, will be equal to impedance. In such a circuit is known as impedance and denoted by Z. That means resistance is R, reactance is basically X, is equal to impedance, which is Z, in short mathematical form. It means that by the ratio of RMS value, the applied voltage to the RMS value of the resulting alternating current, thus Z is equal to Vrms divided by RMS. It is also replaced in ohms. That means the unit of impedance is also ohm, because it is a resistance or opposition to the flow of the charge. RC circuit. Now consider a series of network resistance R capacitor excited by alternating voltage as shown in the figure. That means both capacitor as well as resistance are in a circuit. And as R and C, this is C and this is R in the alternate source circuit. In series, the same current will flow through each of them. If the value of the current potential across the resistance would be IRMS R, and it would be in phase in the circuit with the current IRMS, the vector diagram of the voltage and the current is shown in figure. Taking the current as the reference, the potential difference across the resistance is representing by a line along the current being a line because of the potential drop R is in phase with the current. The potential difference across the capacitor will be IRMS into XC will be equal to IRMS divided by omega C, because we have put the value of XC. As the voltage lags the current by 90 degrees, so the representation of vector IRMS omega C is drawn at right angle to the current line as shown figure. The applied voltage RMS that will be sent this current I in the circuit obtained by the resultant of vectors IRMS R, and this is IRMS divided by omega C. We have root mean square value of under root IRMS R whole square plus IRMS divided by omega C whole square. If we take in the I common over here, we get VRMS equal to IRMS under root R square plus 1 over omega C square. And if we have to find the impedance, which is equal to Z is equal to VRMS divided by IRMS. So we divide it by I over here on both sides. So it will cancel over here. We get the value of Z, which will be equal to under root R square plus 1 over omega C whole square. It can be seen from the figure the current and the applied voltage are not in phase. The current leads the applied voltage by the angle of theta, and theta can be represented by or can be found out by the simple formula of direction that tan inverse is equal to 1 over omega CR. Equation suggests that we find the impedance of a series AC circuit by a vector addition. This resistance R is represented by a horizontal line in the direction of the current, which is taken as a reference. And in the same way, we can see the reactance of XC is equal to 1 over omega C, shown by the line lagging the R by 90 degrees. The impedance Z of the circuit obtained by the vector summation of resistance and reactance figure shows the impedance diagram of the circuit. The angle which line represents the impedance Z makes with R gives the phase difference between the voltage and the current. In figure, the current is leading the voltage applied by an angle. Again, it is theta is equal to tan inverse XC divided by R, which is tan inverse 1 over omega RC. We will calculate the impedance for RLCD. That means if the alternate source was applied across the inductance as well as resistance. Now, what will happen in that case? Drawn by impedance diagram shows the RLC circuit excited by the AC source of frequency omega. The current is taken reference so that it represents the horizontal resistance R and is drawn along the line because the potential drop is IRMS. R is in phase with the current, as the potential across the inductance V is equal to IRMS XL, which we can also represent as IRMS into omega L or divided by omega L. Leads the XL into XL, sorry, not divided by omega L into omega L, leads this current by 90 degrees. So the vector line reactance XL is equal to omega L is drawn right angle to the R line figure. The impedance of this circuit is obtained by the vector sum of R and omega L. Again, the same formula that Z is equal to under root R square is plus omega L square. The angle which we can find out again is by the formula of direction. Theta is equal to tan inverse omega L divided by R, which makes R gives the phase difference between the applied voltage and current. In this case, the voltage leads the current by an angle of theta by comparing the impedance of RC and R LR circuit, it can be seen that the vector lines of reactance XC and XL are directed opposite to each other with R as a reference point. Now, what has been said in this whole two paragraphs? Let us explain this simply by vectorial diagrams. So here is what we have learned about resistance, and we saw that both of these voltage and current are in phase. So let's keep them aside, vectorial diagram, and we have the capacitor. So we have learned about this one as well, that the current is leading by the angle of 90 degrees. So here it is. And in the third case, we have inductor. In this case, we saw that the voltage was basically leading by the angle of 90 degrees. Here we go. Now, what he's trying to say is that if we combine the inductor value with the resistance value, because they both were in series, that means if we are drawing this concept, that means if there's an inductor over here and there's a resistance, so these are in series, that means the current basically follows in the same path. The current has the same direction, whereas the voltages have angle of 90 degrees between them. So how can we find out the resultant of these two, the vectors? Let's call it like this. Let's call it VR. That means which is along the vector of the resistance, whereas let's call it VL. That means which is along the inductor. And the resultant of these two inductors basically is represented by the VRMS, like over here. And this is the angle of theta. We can represent the same line of VL over here. So as you can see over here, this is a right angle triangle. We can apply this trigonometric formula, or Pythagoras theorem especially. So we can say VRMS is equal to, by using the Pythagoras theorem, we can say let me clear it out. VL plus, sorry, square is there, VR square. Now we know the value of VL and R over here. So it is VRMS is equal to, instead of this VL, we can say it is I XL whole square plus I R whole square, because we are using the Ohm's law in this condition. So this is whole square. We know that XL is equal to omega L. So the RMS is equal to, let's take the I common. So this I common over here. So it will be omega L whole square plus R whole square. So if we want to basically increase our steps, we can do it like this: I square into omega L whole square plus R whole square. So this cancel out with this one. This I will go on to the other side, will divide. So VRMS, and the current is also the root mean square value. So it will be equal to omega L R, or we can say this is an impedance. So impedance, we can also represent it like this, and this is equal to, instead of omega, I can write down 2 pi f L whole square, because it was the value of omega, plus R square. So this was the magnitude of the impedance. For the direction part theta, by looking at this diagram, this is the horizontal component and this is the vertical component. So theta will be equal to tan inverse. What is the vertical component, which is you can say omega L, and the horizontal component basically is R, or we can say theta is equal to 2 pi f L divided by R. So this is the formula for the direction of this vector, which is Vrms, by the combining of these two components in a series circuit. Now, keeping that concept in our mind, we are applying the same concept now, cleaning this all out, for the capacitor and the resistance. Now, in this same way, we are going to combine, because the current is same, so I have to keep the direction of the current same. So as you can see over here, the current basically is in the same direction, because in this case, we can draw it like this. This is the alternate source, and this is a capacitor, and it is in series with a resistance. So C and R is there. But what will happen in this condition? Now, in this condition, let's say, if we basically again draw the resultant of these two vectors, like over here, let me draw it again. Which is Vrms for the case of, let's give them a name. So this line was representing VR, the voltage of the resistance, and this was representing VC, the voltage of the capacitor, and this is the combined effect of VR and VC, and this is the angle theta, and this line is representing by VC. Again, by using the same trigonometric formula, but in opposite direction, we can say it like this. Now, in this case, Vrms, V is equal to under root, by using the Pythagoras theorem in this case, VR square plus VC square. So as is in opposite direction, we can say it as Ohm's law, I R square plus minus I x, because it is in opposition, as you can see over here. Now, in this case, let's apply the value of xc. Xc was equal to 1 over omega c. Now, in this case, we can say simply by taking the value of I common, just like in the previous case, V, which is the root mean square value, under root I square by taking common, and what we have left behind, which is R square plus, because this is also square, it is xc square. This square cancel out, will go on to the other side with Vrms divided by Irms. And instead of putting the values of xc, we can say omega c. And we can say that this is equal to impedance. So impedance will be equal to under root R square, and instead of omega, I can say that it is 2 pi f and c whole square. This is the magnitudinal form of the resistance or impedance, we can say Z. For the direction, again, the same concept, theta is equal to tan inverse what was at the vertical component, Vx, or we can say 1 over omega c divided by r. So this is the representation of direction of that vector, which is making between the horizontal component, which is with the resistance, and the vertical component, which is making with the capacitor. And this is how basically we can see that these two are in opposite direction, side by side. Now, the power in AC circuit. Now, in this case, let's what is going to be power in this case? The expression P is equal to V RMS into IRMS. In the expression is true for the case of altering circuits only when V and I are in phase. Otherwise, they won't be in the power form. Case of the purely resistive circuit, basically what was the first one, we have already seen the power dissipation, the pure inductive and pure capacitive circuit is 0. That means they were canceling each other out. In these cases, the current lags or leads applied voltage by 90 degrees, and the component of the voltage vector along this current vector goes to 0. The AC circuit, as shown in figure, and the AC circuits, the phase difference between the applied voltage and the current is RMS, that is, as shown in figure, because both of them are cancelling each other out. The component of V along the current is RMS, and V cos theta is actually, it is in the component of V vector, which is in phase with the current. So the power dissipation in the case of AC depends upon the angle of theta. So P is equal to IRMS multiplied by V RMS cos theta. The factor cos theta is known as the power factor. It can be maximum, it can be minimum, depending upon how the capacitive or inductive the circuit really is. Now comes the series resonance circuit. That means in this case, we have to consider resistance, inductor, and capacitor series. That means if we have an alternate source over here, that means there is the inductor as well as a capacitor as well as a resistance over here. Now, in all of these cases, the current is going to be the same, which excited by the alternating voltage source whose frequency would vary, as shown in figure, the impedance diagram of the circuit, as shown in figure. Now, in this case, all of these inductor, which is represented by L, capacitor, which is represented by C, and resistance, which is represented by R, what do they have a combined effect of? Let's study that. So as explained earlier, the inductive reactance is XL omega L, and the capacitor reactance is XC 1 over omega C, directly opposite to each other. When the frequency of alternating current source is very, very small, XC is equal to 1 over omega C, which is much greater than the XL omega L. So the capacitor dominates over low frequency, and the circuit behave like an RC circuit, and high frequency, which is XL omega C, is much greater than XC, which is 1 over omega C. In this case, the inductor dominates and the circuit behave like an RL circuit. That means if the frequency is, let's say, higher, then the value of the whole circuit will be capacitive. If the frequency is lower, it will be at high frequency, it will be in the case of RL circuit, whereas in the case of low frequency, the whole circuit will be capacitive. In between these frequencies, there will be a frequency where it is represented by resonant frequency, at which XL and XC both will be equal to each other. These conditions known as resonance. Thus, as resonance inductive reactance begin inductive reactance begin equal to the opposite capacitor reactance, each other and cancel each other, and the impedance diagram assume the form of figure. As shown figure, the value of the resonance frequency can be obtained by putting, let's put in the value that XL is equal to XC. XL is, we know that it is equal to omega L, and XC is equal to 1 over omega C. So if we basically take the omega to the other side, it would be omega square is equal to 1 over XLC, and or we can say, taking under root on both sides, omega R is equal to 1 over under root LC, or as we know that omega is equal to 2 pi F. So taking F on one side and taking the 2 pi onto the side, the resonant frequency will be given as F resonant frequency is equal to 1 over 2 pi LC. So in simpler method, we can say omega L into 1 over omega C. This omega goes to the side, will be omega C 1 over LC. Taking under root, omega will be equal to under root LC. Omega is equal to 2 pi F 1 over LC under root. F will be equal to 1 over 2 pi under root LC. Now again, let us revise what has happened in this whole procedure. First of all, there was resistance, which was basically whole in phase between voltage and current. Then there was a case of capacitor in which current was leading by the angle of 90, and then there was a case of inductor in which voltage was leading by the angle of 90 degrees. Then we combined the inductor and resistance to find an impedance, and in the similar way we found the combination of RC, that means the combination of capacitor and the resistance. Now in this case, because all of them are in series, the current will be the same, so let's combine them all, the current at the same point. So in this case, we can clearly see that all of them are in the same direction, and they, the capacitive and the reactive, they both are cancelled, inductive, both are cancelling each other out. So only value which we are getting is of the resistance one. So in this case, we can see the maximum value at this point. That means at this frequency, when both of the capacitive and the inductive values cancel each other out, at this frequency, at this very much frequency, which is known as resonant frequency, we get very high value of current at this point, which is graphically shown. Now, properties of this series combination. The following are the properties of series resonance. First of all, the resonance frequency is given by the formula FR is equal to 1/2 pi under LC. The impedance of the circuit resonance is resistor, so the current voltage are in phase, the power factor is 1. The impedance of the circuit is minimum if the frequency is at to be equal to R. If the amplitude of the source voltage is constant, the current maximum at the resonance frequency and the value of V naught over VR, the variation of the current will with the frequency I is shown in figure. That means no matter how much extra you have of VC or VI, they are going to cancel each other out. It doesn't matter in that case. Then we have, if at resonance VL, the voltage drop across the incidence or inductance, and VC voltage across the capacitance may be greater than the source voltage. That means even if they are greater, it doesn't matter, they both are going to cancel each other out. Now for the case of parallel resonance. In the case of parallel resonance, figure shows the LC parallel circuit, or we can say R also in this case. Let's draw it R as well. So here is the alternating source, and there is an inductor, and there is a capacitor over here, and there is a resistance over here as well. So this was in series, but we are going to draw in the case of parallel. So we draw it in another way. Now in this case, it is a coil over here, a capacitor in parallel to the coil, and there is a resistance in parallel as well. Now this is a parallel circuit series or parallel resonance series. In the same way, it is excited by the alternating source voltage of frequency. Let me clear it out so that it's clear. Whose frequency would vary. The inductance coil L has a resistance R, which is negligible small. The capacitor draws the leading current, whereas the coil draws the lagging current. The coil resonates with the frequency of resonant frequency, which makes XL equal to XC. So the two branches of the current are equal but opposite, hence they cancel out. With the result, the current draws the supply 0. The actual practice, the current is not 0 but minimum value due to the resistance of the coil. Now the same thing happens, that there's a resistance, there's a combination of resistance and capacitor. So let's combine this inductor and resistance first, and then we combine the resistance and capacitor again. But now they are not in series. That is why the current does not have to be the same. The current does not have to be same. Now in this case, in the case of basically parallel, the voltage has to remain the same. So let's make the voltage same. So we can say the current basically are in opposite direction now in this case. So let's cancel out this current. And we can see very clearly that it is again we are getting the current and voltage in this case, but the current is very, very small at this point. So it has to be very, very small at this point, which is the resonant frequency at this point. At this point, the current is very, very small. At the other points, all other point, it will be maximum. But at this frequency, very much this frequency, the current is going to be almost minimum. So let us read the properties of parallel resonant circuit. The resonance frequency is given by, again, which is FR is equal to 1/2 pi under root LC. At the resonant frequency, the current impedance is maximum. That means the stopping power is maximum and it is resistive. At the resonance, the current is minimum. It is in phase the applied voltage. So the power factor is 1, the variation of current with frequency of source as shown in figure. At resonance, the branch of IL and IC may be larger than the source current. That means no matter if it is greater, they both are going to cancel each other out at the end. Now, at the end, we can simply say that we have understood the concept of all of the resonant RLC circuit properties, as well in series, as well in parallel form. I truly enjoyed today's lecture. Inshallah, we'll continue this session. Until next time, take care of yourselves. Bye-bye.